on the things that he did as part of his dissertation. And also, I'm going to show results from Kevin Silva, who is currently a PhD student working in my group, and he's really taking that foundation that Wenja put together and bringing it for detailed computations of ships in extreme seas. So the research objective is to numerically predict ship motion in extreme seas. And my research has traditionally used computational fluid dynamics, and the flavor of this talk is how can we use that together with machine learning. And just to start making some general comments about how I see this coming together. So I believe that machine learning is, there's a lot of excitement around it today. It's based, there's new methods that are emerging. A lot of them are based on old numerical techniques. I know that in our curriculum here in our department, we learn about neural nets in required courses at the undergraduate level. This goes back to the 90s when they're in ship design courses. Regression methods have been around everywhere for a long time. But this resurgence of interest has really brought it into the forefront of what can we really do with the data that we can observe. And so I'm going to start in the beginning by giving you an idea of how I look at using machine learning within the marine hydrodynamics context. And then in part two, I'm going to use machine learning in two different ways in this talk. The first is I'm going to build a neural net that is a generative model of the phases of a wave system. And this will not be a uniformly distributed phase, but it's going to be a phase set that leads to extreme waves or extreme motions, whatever dynamical process you're interested in. And I'm going to test this on linear waves, on second order waves, and a nonlinear roll ODE. Then in bullet 3, I'm going to use machine learning in another way where we will just replicate nonlinear response. So this will be, if I'm given a wave system, a time history of wave, can I predict the 6th degree of freedom motion based on a neural net? And I'm going to show this for only in 2 degrees of freedom for the ONR tumble home section in beam seas. All right, so when I think about extreme motion in the ocean, capsize, broaching, extreme loads, this can extend to wave loads on fixed ocean platforms. The starting point is that the ocean is random, which means we're going to want to be able to understand the distribution of response. Extreme rents are rare by definition, and the interaction is nonlinear and complex. And we even, our understanding of what happens in the extreme events is limited. If we try to recreate them at model scale, then we have in our wave basins, we have scaling effects that we have to be concerned with. They're certainly complex because we have the human operator operating a ship in an unknown seaway based on their perception of the environment that they're in. And then the wave environment itself is incredibly complex with the interaction of waves, breaking waves, multi-directional waves, and wind and turbulence. So incredibly complex problem. And there's still a lot to learn about what happens in these necessarily rare events. And so what I've drawn here is just some time history. So if we wanted to really, if we had a really fast running numerical model of the dynamical process of the ocean with a ship in it, then we would have to run it a certain number of times for an extremely long length of time to be able to statistically describe the response. And there's really nowhere to get there from here because of the expense that would be required to be able to do an exercise like this. So my viewpoint is, how can we use CFD, which does have the promise to resolve computational fluid dynamics, to resolve many of the complex and nonlinear aspects of the extreme events? It does. We can have moving rudders and propellers. We can have breaking waves. We can do some interaction between the wind and the wave, but it's incredibly expensive, and we're limited to short exposure times with the CFD. Just to give you an idea, we can do several minutes of CFD simulation in the course of several days on supercomputers. And of course, you can use the parallelism of the HPC. So you can do, say, order of magnitude 100 samples for several minutes each to be able to understand something about an extreme event. And so if you can harvest that much data, how can you generate the wave environment that leads to this extreme response? So what I've highlighted here, I can't get my stylus. So in the red boxes, you have the, I would like to perform CFD only around small or short time window events, and then learn as much as we can about what happens in those short time window events. Okay, so now how does machine learning come in? Well, just in general, we all probably have this depth of understanding of what machine learning is. A lot of us, we do things explicitly where we write computer programs. We put a set of instructions in a text file and compile it, and then we ask the computer to follow those instructions. That's very good. But in the machine learning context, we want to say, well, we would like to learn the instructions from observation. And so here's a cartoon of X independent variable, Y dependent variable. Blue circles could be some data. And if we have a new sample X, we'd like to be able to predict what Y is. And so we collect a data set of X, Y, and then we develop some sort of algorithm. We choose an algorithm, and then we build a specific model for this data set so that if we happen upon a new X, we can get a new Y using the variable Y hat. In the context of, that's very general and abstract. In the context of the machine learning for extreme ship motions, I'm going to build two machine learning models. One is where the input to the model is going to be a phase set, and the output is going to be more phases. So I'm going to learn the distribution of phase at a given rareness level, so that I can sample that distribution and generate more random but non-uniformly distributed phases. The second way that I'm going to use machine learning is I'm going to build a model where the input to the model is going to be the wave elevation as a function of time, and the output will be the ship response. The two are linked. If I can generate random waves that lead to an extreme response of a certain level, I can sample it, and then I can put it into the second machine learning model and generate the ship response. All right, this is a general schematic that sort of lays down the pipeline of how the process of building a model and then deploying it looks. This is something that was not put into our curriculum in the 90s when we talk about neural nets, but this is definitely a product of all the interest that we've seen over the last decade. And so, very simply, you collect data, and the pre-processing is a very important step, scaling the data, converting the data to the most important features. And in this data collection step and pre-processing, you would like to know something about the physical process. Okay, you can hire a data analyst that knows nothing about extreme ship motions. They can do this, but if you know something about the ship motions, then you're going to be able to do this very effectively, and it's a very important step. Now, the model design is, how do you want to actually, what type of model, machine learning model do you want to choose from, of which there are many, many, many. Then you train the model to really make it specific for your data set. And then it's important to be able to evaluate the model. And you can go around in a circle until you're satisfied, and then you finally can deploy the model. Okay, another important general characteristic that you need to adopt when you're performing machine learning is really understanding this trade-off between underfitting and overfitting. This has a lot to do with how you evaluate different models. It has a lot to do with how do you determine the quantity of data you need to train a model to a given level. And we see three figures here. On the left, we would call that an underfit model, where we're not resolving as much of the character of the data relationship that we might like. In the center, we call that a good fit. And then on the right, we call this overfit, where the model is learning what you might call noise in the data. And what I've just described is very, very general and very subjective. There are algorithmic ways to encapsulate this, my subjective description. And one thing that is important to do is you take the data that you have available to you, and you only use a portion of it for training, and then you take the remainder of it and you leave it as unseen, and you use that as validation. So you'd perform regression on, say, half the points, and then you evaluate the regression on the other half of the points, and you see how well the model is, and then you can develop different models, and this would be a way for you to assess how well the model is working. Okay, now in our work in the talk today, we're using a class of neural networks called recurrent neural networks. They're a class, there's many of them. If we look at the top, this is a schematic of a recurrent neural net. What it is in the green, X, T is an index, meaning we can have an array or of data, and the output is Y. And so you put input into the blue box, you circle around, and Y comes out the other end. Very much black box. If we unfold this, what you see is that you have data flow where you have X is a sequence of data, as well as the output Y, and at any index, the output Y, it depends on the blue box directly that it's directly connected to, but you can also see sort of this flow of information from multiple inputs going into the output. And to give you an idea, this would be a generic architecture. When it's time to train the model on your specific data, what that really means is optimizing parameters within each blue box so that the output that's predicted by the model is close to the output that's in the original data set. And if we look at a simple recurrent neural network unit, a single blue box, you see you have information coming from the left, you have input coming from the bottom, and that information goes into for example, this is a simple unit, a hyperbolic tangent function, which then goes into the sigmoid function for your output. And really, the training of the model means optimizing the W and the B so that the output predicted is as close as it can be to the output in the original data set. On the right here, I show different architectures just to give you an idea that there's many, many ways to do this. You stack these in layers if you want to do deep learning, but you can think of the input as many-to-many. So you have you have a large sequence of data that's going to predict a large sequence of output. Or you can do many-to-one, where you have a sequence of input that feeds into a single output. Or you can do the inverse, where you have a starting point and it predicts sort of the domino effect of a bunch of outputs. Or you can do a very large number of permutations of these type of RNN networks. And we're going to use, for the unit, we're going to use a long short-term memory unit that is, it's more complicated than the simple one I've shown here, but it's doing basically the same thing. Okay, so let's move into talking about machine learning to generate extreme waves and ship responses. So our starting point for this is, let's consider a process that can be represented as a Fourier series. Now, if eta is wave elevation, then this would be sort of a linear wave description of the ocean surface. But if I were to get rid of t, then I just have a Fourier series in space, which we could represent a nonlinear ocean surface because it's sufficiently smooth. But we will have amplitudes A that we can consider as coming from a wave spectrum, together with F being the frequencies, K being the wave numbers. And those are all determined by the wave spectrum, and we'll consider the phis to be random. Now, if we don't know anything about the ocean, then, or if we're considering all scenarios, we would say that that Fourier phase is random and it's distributed uniformly. We can sample the uniform distribution on the range minus pi to pi, and we can generate any number of sort of seed vectors for a given number, capital N Fourier components. And we then can evaluate the sea surface. Then if we have the sea surface as a function of time, there's different things we can do with it to predict the response. So you see in the schematic here, we have a random seed. We can evaluate the environment, and then we evaluate the response. Now, there's many, the two boxes in the center on the right, the environment realization and the response realization. For the environment, we can use this random seed as an initial condition in, say, a higher order spectral code or a higher order wave code and allow it to evolve nonlinearly. We can then take that linear, nonlinear seaway, and we can apply that to a nonlinear ODE describing ship response. We can apply it to a potential flow model, linear or blended or nonlinear. We can apply it to a CFD. We can put it into an experimental model basin if you wish. But what I want to do from the question I have for the machine learning ask is, how can we generate wave environments to lead to an extreme response of the nonlinear system, however you wish to define the nonlinear system? And the inspiration from this is a language model. And so if you've ever wondered how Google is able to determine what you're really searching for, you can do this for letters or you can do this for words, and of course it'd be different in each language. You can calculate the probability of a string and sort by probability, and then that's how it makes suggestions. And this was a search that was done when Wenja was creating his defense about a year ago. I wonder if the list would be the same today, because I think that they update their probability tables at a certain frequency. And the way they're able to do it so rapidly is if you use the chain rule, you see you can say the probability of a string is the probability of the first word, times the probability of the second word given the first word, et cetera, et cetera. To be able to do this, you have to encode the words into a number. Well, we use this same motivation to say, well, what is the distribution of different phase sets? And if we can learn this, the relationship of the probability of a phase given the previous sequence of phases, then we can sample this to generate new ones. So this is a generative machine learning model. And we view the phase angles as an ordered list, similar to words in a string, and then we can sample the learned distribution to generate new wave environments. So let me show you how this works schematically. Let's start at the top, data set 0. Let's just generate uniform distribution of phase angles, and we can generate as many of those as you wish. Generate a large number, evaluate them, whether we just want to say what is the maximum wave in the wave elevation in the Fourier series. We can take the Fourier series and put it into a nonlinear roll ODE. We can put it into a higher order spectral code, whatever you wish. And then you can evaluate eta sub r as just whatever response you're interested in. We can then sort them and filter and say the phases that generated the response PDF and D naught are uniform. But if we were to filter and only take an upper quantile, let's say in this case the top half, then the phases would no longer be uniformly distributed. So data set 1 is the filtered data set 0, and we want to take all the phases in data set 1 and try to learn the relationship between them. And that's the target extreme generator, the TEG. That's the long short-term memory neural net that says, given a sequence of phases, what's the next phase? What's the distribution of the next phase? And we can sample that, and then we can build, indefinite number of, or we can collect a large number of samples from this non-uniform distribution that we learned from the original uniform distribution. And now we call this bootstrapping because now we can do this recursively to generate TEG models that correspond to higher or larger and larger responses. And I'm going to show this on three examples. The first is, let's consider just I would like to generate random waves that have a wave elevation that's greater than 3 sigma. And we have, this is some sort of John Schwab spectrum. And we say, can we just randomly generate wave elevations or wave time histories that have an elevation that are greater than 3 sigma? We put, for a Gaussian process over on the right, probability of the wave elevation being greater than a threshold. And so the threshold is 3 sigma. This is like, 1 out of 500 or something wave time histories would have it if you sampled uniformly, but we want to be able to know that each one is going to exceed the certain threshold. Now, in this series of 8 figures in the bottom half of the slide, let's start in the upper left. I'm showing in the reddish color, this is the histogram of the training data. In the blue label generated, this would be samples from the learned distribution. Okay, so if I build a model with the data in red, and then I sample that model, I can get data that looks like blue. And note that we're going to be what we're really interested in is exceedingly larger events. So although right at the sort of the sharp cutoff in the way we filtered the data, there is some difference between the two. If you look at, say, the top half of the data set comparison, it's quite, it's much improved. We can do this here. Wenja did it 8 times to get out to a sigma, 3 sigma distribution, and you can see that the process continues on, and it's bootstrapping itself. Now, in this histogram, we're interested in the extreme events that have low probabilities, and they're out in the tail. So the nice thing about studying the linear wave is that we know what the tail looks like. And so if we just plot in the log, semi-log space here, you can see the Gaussian PDF tail and the generated tail in blue. And let's say if you take the square root of the horizontal axis, the 16 gets you to a 4 sigma. Out to about 4 sigma, we have very strong correlation between the two. And if we, this would depend on the quantity of the original starting data set, as well as, we could continue to bootstrap further and further. Okay, now let's do a less trivial problem. Let's talk about second order waves. And for our surrogate for nonlinear process, we're just using the Forrestal second order wave, or the second order wave theory that was presented in Forrestal 2000. It's very nice because you have the wave-wave interaction, you have a first order and you have a second order correction to it. And here we said, can we generate waves that lead to more than 2 sigma? And this, you see a very similar behavior between the language-inspired model in the original data as we bootstrap out to things greater than 2 sigma. And something that's really interesting is in this slide, what I'm showing in figure 23, we have the distribution of phases. On the left, we're looking at sort of a 2-dimensional histogram from Monte Carlo, and on the right, it's from the machine learning model. And if you look at these axes, you see we have the phase angle minus pi to pi. Then we have the Fourier index, so they're ordered in frequency. And then then it's the histogram vertically. And so you can see how the phases are distributed. And you can see how the machine learning model for phases corresponding to largest waves greater than 2 sigma in the nonlinear model are the character is very similar between the Monte Carlo simulation and the TEG. And now that we have the TEG, we can sample it as often as we want, and each time we sample it, we get something here. We're showing 1,000 realizations, something that's greater than or near this sort of 2 sigma event. Okay, let's go. I have 2 more slides on this, on the generative model. We then took it and we said, let's apply this to a nonlinear roll equation. So this equation has a nonlinear restoring moment, the delta GZ, and it has a nonlinear damping, the D function of theta dot. This is a nonlinear roll model from the literature, and it's excited to both random wind and random wave. Both the wind and the wave are described by Fourier coefficients. We put the phase angles of both of the Fourier series into the same data sequence. And we said, how can we use this to generate wave environments that lead to roll greater than 28 degrees? And so we used the exact same process that I described for the linear and second order wave. And what I'm showing you here are time histories. If we used Monte Carlo simulation and do 20,000 random wind and wave environments, about 240 out of the 20,000 would exceed this 28 degree roll angle. But when we train the TEG, here's just, 833 realizations. We can get as many as we wish, and they're random. Now, what is an important question to ask is, what is the cost of the training data? What is the cost of building the model, of training the model? And I'll speak about that in different ways through the remainder of the talk. But Wenja did work out a very nice way to look at the cost for evaluating different this target extreme generator framework. And so what we have in the figure here is the logarithm of the cost of the machine learning model normalized by the cost of the Monte Carlo simulation. And without going through the definition of everything, I think you get an idea of what the cost of the Monte Carlo simulation is. It's exponentially more expensive for rarer and rarer events. And then the cost of the target extreme generator, there's really two parameters in it. One has to do with the rareness that you're interested in, which is beta 1. And then beta 2 has to do with the relative cost of the evaluation, the number of training points, the cost of each training point, the cost of generating each new sample. And what you can see in this semi-log space is that there is a rareness threshold greater than which the machine learning model is much more cost effective, and it increases with this crossover point increases with the training cost of the underlying model. So if you want to do non-rare events, then building this target extreme generator is not the right thing to do. But when you want to go to rarer and rarer events, this indicates that it is what you want to do. Okay, this concludes the part on the generative model. Now I want to say, can we use machine learning to learn ship motions? So the idea here, if we have a wave time history, can we put it into a model and predict the ship motion? We just spent 20 minutes talking about how to generate wave environments. Now I would like to link it and say, can we predict ship motions? And really the way that we're going to do this is, here I've laid out another LSTM network where the input, instead of a sequence of phases, we're going to have wave elevation time history. And then the output, the y-hat, this will be the motion time history. And we're going to do this for a two-dimensional CFD simulation. I'm going to start by talking about just can we learn the behavior in random waves, and then I'm going to talk about can we learn the behavior in more extreme responses. And so let's see if we can learn this, the 2 degree of freedom motion in random waves. And so we're doing a C state 7. We're doing the ship. This is the ONR tumble home ship at full scale. We perform 150 simulations, each of 6-minute length, so about 150 hours of full-scale exposure time in this C state 7. We generate a neural net based on the LSTM network. We're doing everything with Keras, which is a front end for TensorFlow. This all happens in the cloud with Jupyter notebooks, Python notebooks, and all the training happens on GPUs as part of the Google Colab platform. And the specific model that we built here, it's 2 LSTM layers. Each layer has 50 cells or units, and we have a final fully connected dense layer for generating the output. We split the data 80-20, which is a rule of thumb. So we use 120 of the data runs for training and 30 for validation. And then I say here, to train the model, it takes about 17 minutes on a GPU. What I'm plotting here on the bottom is the training loss, what this is. So the loss is an error measure of the error between the predicted output and the given output. And so we can, y hat is prediction, y is the original data. We can do this loss function during training. We definitely do that, and that's what's plotted here. We can also calculate this loss function over the set of points that are in the validation set, which are unseen by the model during training. Each epoch is we optimize the weights in the network to minimize the loss function. And you sweep through the network, changing the weights, optimizing them to minimize the error in the loss function. So here you can see that you have the loss over the first 2,000 epochs. You have a significant decrease in the loss function of the error, and then it begins to stall out, and you keep training, and the loss function doesn't improve much. Now let me show you some sample time histories. These are on validation runs, which are unseen by the model during training. These are 4 of them, 4 of the 30 validation runs. And these, you can see the blue is the prediction and the red is the ground truth. This is over the full 360-second runtime. And I think you would say that this looks like the neural net was able to learn a lot about the ship motion. And what we do is we can, off the validation run, we can compute the L2 and the L infinity error for each degree of freedom, heave, and for roll. And then we can do a scatter plot like this. So if you look on the left, we're plotting the L2 error of roll and the L2 error of heave. And we have 2 sets of data. The blue would be the training data, and the oranges would be the validation data. If we go, and so you can get an idea, so that, if you were to do the centroid of those points, you have less than 1% L2 error in heave relative to the beam, and you have about a degree of L2 error in roll. In training and in validation, it's maybe 50% greater than that. If we go over and look at the L infinity error, which is what at every instant, looking at every instant in time, what is the maximum error over all instances in time, we see that obviously the numbers are going to be larger. We see something like a 5% error in heave maximum, and then we see the roll maximum error is something in the 4-degree range. Now, in the lower right figure, what we've done is we've built networks off of different sizes of training data set. And in this box and whisker plot, if you look at just 20 training samples, we have the RMS error in heave, and you see a box and whisker with an outlier that's quite low. That represents the training data. And then next to it, the larger one, you see that is that model evaluated on unseen validation data. As you increase the number of training samples, the RMS error on the training data increases because you're asking the net to do more things, to span a larger set of data, but you see that the validation error drops, and particularly between 20 and 60 samples. And so this is a way for us to determine how much data is required to get a certain level of accuracy out of the model. And of course, the model is never going to be any better than the quality of data that it's given. If it is better, then you're lucky, and that's not necessarily what you want to rely on for your engineering analysis. Okay, one last small section here. I want to talk about how we use this system identification neural net for predicting extreme roll. And I'm not going to use the TEG for generating random but rare Cs. We're using something called the a method based on critical wave groups. And there's a series in the literature of papers. We need to certainly reference Spiro, Themikis, Anastopoulos, as well as a larger collaborative network throughout the world that uses critical wave groups. And the idea is, in abstract, if we can understand the probability of a wave group, however we wish to parameterize it, and we know the probability of the ship motion when it encounters the wave group, then we would like to know what is the response given an encounter condition in a wave group. If we can do that, we can define the probability of exceedance as the integral over the sample space of groups and encounters, integrated over the region of which the response exceeds a threshold. That's what that one vector function is the indicator function of whether we've exceeded a threshold. And so to use this method, we need to be able to understand what are the probabilities of wave groups in the groups that lead to a threshold exceedance, and then we need to know the probability of an initial condition. The way that the method is developed, it's done primarily with using the response defined as a Markov chain wave group, where each wave in the group is described by two parameters, its period and its height. And then you also have the parameter, which are what are the number of waves in the group. And there's different ways that you can parameterize the wave group, obviously, and they've looked at several, if not many. And they use a nonlinear ODE to predict the response. And if you do that, then all you need is the wave group and the initial condition. If you'd like to use this method with CFD or even an experiment, you can't start for a random initial condition. You can't impulsively start in a wave group like this. We need to embed it naturally into an environment because we need basically we need the initial condition on the Navier-Stokes equations. So what Kevin Silva and I have come up with is we embed the Markov chain in an irregular wave with a hyperbolic tangent blending function. And then so for a given wave, we can generate any number of irregular waves, each of which leads to a different encounter condition at the time of the Markov chain beginning. So that way we can evaluate what is the response given an initial condition in a specific Markov, in a specific wave group. Now, how this works with the machine learning. Let me show you sort of the flow or the framework of how we have the element from critical wave group, which I gave a very, very brief or poor introduction to what it is. We have CFD, which I think a fair number of us understand how that works. It's basically numerical representation of the approximation of the Navier-Stokes equations is something very similar to performing an experiment. But we generate a random C wave, and we can simulate the motions with CFD. And since it's so expensive, we're not going to know very much about extreme motions, but we can gather some information about the state. What does the PDF of the state look like in a random C wave? From the random C wave, we also generate the Markov chain wave groups. How? Well, the Markov chain, given a wave of a given period and height, we need to know what is the distribution for the next wave. And that's how you build up the Markov chain. And we collect statistics from the random C wave so that we say, okay, given a wave of a certain height and period, what is the most likely next wave, or what is the distribution of the next wave? We then embed the wave group in the random C wave, and we can simulate these in CFD. Now, to find that indicator function, we need to know we have a threshold hunting problem. So we generate a wave group of a given central wave height. We evaluate it in CFD, and we see where we are on the threshold, relative to the threshold. And then we have to go back and iteratively change the central wave parameter until we get arbitrarily close to the threshold crossing. This is where we bring in the CFD. We say, all right, let's evaluate several Markov chain generated wave groups embedded in an irregular C wave for a given initial condition, and then we'll use those to train the neural net and then evaluate the neural net at a much lower cost point to really find the indicator function that says what is the boundary that leads to a threshold crossing. The tool that we're using is OpenFOAM, where we have some customization for the body motion, the wave generation. We're using the same grid setup, but this time we're really, instead of looking at random Cs, we're looking at really the extreme Cs. Kevin ran, close to 10,000 runs, each of 2 minutes long. And this is an example of the roll in the heave with the CFD in black, and then he generated different variations of the neural network model. And you can see this is on unseen validation data, how close the two are. It's obviously not perfect, but from the standpoint of predicting the stream, there's very, very good correlation between the two. If we look over a very large number of samples, what I'm showing you here on the left, if we take a sample and we calculate what is the RMS roll in CFD, and for that same wave environment, put it into the LSTM model, what is the RMS roll? We can place that data point on this graph on the left. And if the neural net were perfect, everything would lie right along that line. Also in this graph, I'm showing neural nets built with different quantities of training data, whether we use 50, 100, 200, 400. And you can see that as you increase the training data, the points begin to cluster around the line that goes through the diagonal of the graph. If we look on the right, this is the PDF of the roll motion. The black line is from the CFD, and then the other lines correspond to different quantities of training data in the different neural nets. And when we're looking at extreme motions, we don't care so much about what happens near zero in roll. We care about what happens in the tail. You can see that the LSTM 50 doesn't do a good job past 20 degrees. So let's move and look at the maximum roll angle. And so what I'm showing on the left is for each sample, we can compute the maximum roll with CFD. And then if we take the same wave and put it in the LSTM, what is the maximum roll angle? And again, as you increase the number of runs in training the model, so that'd be the red, they're clustered more closely to the diagonal line. But most interesting, if we look over on the right, we're looking at the tail of the PDF for 50, 100, 200, and 400 number of runs in the training of the model. And you can see that the tail, out past 40 degrees or even past 45 degrees, the PDF does of the LSTM model is much closer to, quite close to the underlying CFD PDF. And just 2 more slides. So to put this all together, we can now use the complete critical wave group method for a range of thresholds. And this is the probability of exceedance of a given roll angle. The black line is the Monte Carlo. And then the red squares, this would be just not using the LSTM, but using only the CFD to find the threshold. And then in the purple, green, yellow, and blue, that says if we use some CFD to train a LSTM network and use the LSTM network to help drill in and find the threshold and define the critical wave group, you can see that once we have models with, say, greater than 200, the LSTM 200 and 400 models do a very good job of predicting the probability of roll out to large angle. Now, I don't know where the Monte Carlo simulation curve, it may stop around 30 degrees just because it gets exceedingly expensive. If you look over on the right, this is a characterization of the simulation time for the different methods. And you can see in semi-log scale, you can see the sort of the exponential growth and cost of simulation if you want to use Monte Carlo, especially for exceeding roll angle. And then the other curves, these are the CWG cost per threshold crossing. If you say that the 200 run CWG is sufficient, it's order 100 in terms of simulation time hours for any threshold crossing, even out to 55-degree roll angle, whereas you're looking at 10 million hours if you want to use a Monte Carlo method. Okay, so the machine learning, I say, offers many ways to extend the value of data. In CFD, we're endlessly calculating hundreds of millions of unknowns and then predicting, say, 10,000 time steps of the 6th degree of freedom motion. So we're in CFD, we know a lot about throwing away data. What machine learning offers is a way to say, how can we reuse data to replicate it at a much lower cost point. The quality of the prediction is certainly limited by the quality of the data. This is an obvious statement. And then we say that the random phase generator is able to bootstrap out to extreme conditions. We showed that for linear, second order, and nonlinear ODE roll. And then we know also that system identification is possible. But each model here, I didn't show this clearly, but the model should be limited to specific ranges of wave parameters. That means we can't build one, if we have a ship, it would be very, very hard to build a model that would say what are the 6th motions in all sea states that it's going to find throughout its entire life. You would like to build a model for a very narrow set of conditions so that the data requirements are tenable to build a model for that specific environment. And then I want to just conclude and make sure I give acknowledgement to some of the most important pieces in this work. That the critical wave group method. There's a large set of papers that have been published on it, of which I've included a few of the ones that we use in putting specifically this work together. I want to give acknowledgement to my PhD student Wenja, who completed his thesis last June in 2020. And we have a couple of papers under review right now with this work. Also, we haven't presented them yet, but Kevin Silva will be presenting some of the work that I've given a look into at the upcoming Marine Conference that's going to be held virtually, but was to be in Scotland, as well as the STAB Conference, which is coming up in early June, which was to be in Poland, but will be held virtually. And so with that, I'm very happy to conclude and answer any questions.
Thank you very much, Kevin. Very interesting. What's happening with that analysis? Yeah, thank you. Questions? You can just unmute your microphone and ask question, or raise hand and then ask questions through me. So do not, any questions? Any questions? Any questions? Yeah. Okay. See, let me start some questions. Kevin, I understand each technique needs its own language, and also some translations would be great from one field to another field. So it's not kind of very standard in mathematics, but potentially if a function we want to calculate value of that function is complicated, then instead of computing that function, we can compute it at several points, certain points, and then to use this table to guess, or not to guess, but approximate the actual value we need. We just take the function f of x and we calculate it with certain step. If we calculate with the uniform step, it's something like Monte Carlo method you mentioned, or if we calculate with arbitrary step, better to say. If with uniform step, it's something we are saying just we do not have no idea what that, and this is why we calculate everything with as small step as possible. But if we have knowledge about that function, then we can calculate in proper point, proper distributed. That is kind of the we bring knowledge to this story, and then we do not calculate this function anymore. We just forget about how it's calculated. Is it by formula or by CFD or by something else? It could be just the wave resistance as function of I don't know, the significant wave height, say. That's all. And next time we just going to that table and saying, yeah, that is the value. I understand it's something like it's here, but it's in higher dimensions. So it's functions like first example you showed. There is could be 100 waves. So 100 that random phases, and you consider then say a response. Only also certain response like maximum roll angle as function of that random phases, and you try to find that phases which give the maximum response. So it's already something like optimization or minimization function. Right? So to do that, to do minimization, you need a certain model, right? Or some people call it, I believe, meta model, because it's something simple. It's something simple. For in ship hydrodynamics is always linear model. Linear but fully, no, not fully potential, just linear potential model. Yeah. And then if so, then we can we can do the same things by that linear model and find, not find, but identified regions where potentially the phases are in that phases provide highest, say, roll angle. And after that, we can go there with CFD and to find what's that. But again, even with CFD, even we localize this area region, we still need to behave wisely. Because without that, we can spend time, in some sense, for nothing or not very efficiently. And I understand that machine learning, it's a set of techniques which helps you or guide you how to find the how to minimize that function or maximize it in a certain way. Is it right? Or because I'm saying from the say mathematical perspective, so is it kind of that, or it's much more complicated, or it's just very different from what I said?
Well, I think that the things that you said are very true. You know, curve fitting it sometimes is the right thing to do, and you could consider some types of curve fitting machine learning. But I think what you described certainly doesn't encompass all of the techniques and activity. So there are, it's very broad. You know, it's almost as broad as mathematics, maybe, if you'll say. Many people use it in different ways. I see the future of having familiarity with certain techniques so that you can interface with the people who are specialists. But the value center for the engineers, specifically those in naval architecture and marine engineering, are knowing more and more about the physics, understanding their gap in knowledge, and then saying, can I use a machine learning model, generate some data, and use a machine learning model to help me close the gap, and then always being aware of what is the uncertainty of this model that I'm using, and what are the limitations or pitfalls that I can be subjected to if I use the model. So that's sort of my viewpoint on it.
Mm-hmm. Any other comments, the additions, especially from people who are using models?
I have a question.
Mm-hmm.
Thank you, Kevin, first of all, for a very interesting talk. I understand part of what you're doing and the practical applications. One thing I came to think of, you had this slide 24, you showed some nice examples on how good machine learning can predict, say, a given time history. And I think I understand this, how you do it, but how do you imagine if you would like to make use of it, you can say for real-time decision support, say that, so you would like to predict ahead of time, ahead of current time. How do you imagine this to?
Yeah.
And can you obtain equally good results?
Yeah. Yeah, very good question. Thank you. So to predict the future, you would have to have an idea from the system identification of, can you predict the wave in the future? And then if you knew the wave in the future, you have the model there to be able to predict the motion. One thing that I'm very much interested in that we're doing together in our group is, and it's part of a family of methods called physics informed, where if you have a low order model of the motion, that's actually an input into the neural net. And the neural net then doesn't predict it could either predict the total motion, or it could just learn and predict the correction to the low order model. And the nice thing about that is that in the conditions where the linear model does well, the correction is going to be small and you have the linear motion. In the more extreme cases, you're asking the model to only learn the dynamics in the most extreme case. And really, you know, there's a lot of analogies between machine learning models and humans, and this could be you only want to learn what you need, right? You don't want to try to learn everything at once. You really only want to focus and learn the things you need. So that's why we like the idea of a physics-informed model where you only have to learn a correction. I don't know if that answered your question or not.
Partly, yes, but it's yeah, it's interesting. Thanks.
Yeah, it's anybody else want to learn more from the first hands about the machine learning? Kevin, I understand the. I'm just using time. I understand the same. Or not the same, but similar techniques can be used for many other problems, like offshore structures, right? And wind turbines, offshore wind turbines, and also for, I don't know, for some events which are not related to fluid dynamics. Could be like that vaccination, COVID, and pandemic and other things. Is it right, or is it something specific? There is something specific in the field of naval architecture.
Yeah, the techniques we're using are developed in a very abstract setting. Like I said, language, strings, predicting traffic patterns on Google Maps. You know, a very broad set of things are predicted with these credit card offers that you get. The ads that you see, all these are, you know, using very similar underlying techniques. And we just make them specific for the naval architecture, the ship motion problem.
Okay. But if to think about, say, that is the for open water. If to think about, say, Arctic, ship in ice. Sorry for asking it. So the ahead of other events. So the but is it about the same, right? So you. Or there is some specific because there are extra conditions, ice conditions, and then you can analyze that condition, impact of that conditions on the ship speed, say, or forces or loads on the ship, and for example, instead of that phase random phases, you can introduce the distribution of ice in that region, or the ice field, some parameters of ice field, and to study how it's happening, to learn, to teach your system how to solve that problem. So the is it something like that, or?
Yeah, that's right. If you have the data of ice thickness in, you know, response, whatever motion or power required, or drag or wave height, yeah, you can learn the relationship between the two if you have enough data that spans a parameter range and response range.
Okay. But it's still about the kind of finite number of parameters, right? So it's not like a functional dependence, right? So that is the if you say it's ice thickness, distance from the ship to the ice, then it's say 2 parameters. But potentially there could be many of them, right?
Yeah.
because and then it would be much more complicated to do that, right? But is it possible to you said the machine learning say by CFD or by using CFD, not by using CFD but through CFD, but the same as you said also can be done by experiments in the tank or in a field, but also kind of combination of all of them. Right, so the validation, especially validation, could be important in terms of the kind of cross validation. So prediction by CFD and validation by experiments, or prediction by experiments and validation by C trials. So, for example, yeah. That is it's a multi-level research. Yeah. Hussein, do you have your question?
Yeah, thank you, Kevin, for the presentation. I mean, if we have in numerical on CFD, if we have truncation error or a numerical diffusion, what are the factor errors that you have in machine learning to predict exactly what's happening?
Yeah. So, you could use. There's different ways you could use it if you, if the data were to be for different different grid settings. What are the result, and you want to learn the relationship between the two. Discretization is intrinsically a local thing, although because you build different grids, you typically look at it from more of an integral standpoint. So there are people that are using neural nets to try to understand the discretization error locally, and then use that information to adaptively refine the grid to control the final discretization error.
I'm just continuing that question. Is there techniques to kind of account for that numerical noise or numerical uncertainties in addition to physical uncertainties?
Yeah, certainly, because all data, typically data has noise in it, and so there are classes of models that explicitly use the noise in the construction of the model, so that your prediction has an uncertainty on it, and it doesn't try to overfit the data. So there are certainly techniques that that's the fundamental starting point of the construction of the model.
Okay. Last chance to ask questions.
Sorry, I can't really figure out how to raise my hand. I can do it like this.
I cannot see your hand.
No, I couldn't figure out how to do it.
Okay. Yes, please ask question. Yes.
Okay, but thanks for a very nice talk, Kevin. I had a question. So, I mean, this final example you gave is a 2D rolling body, and I think I don't remember the numbers, but I think you spent a lot of computational time to train the model on this. So I guess my question is just more in the sense that if we're really interested in a 3D ship and going at let's even just say 1 speed, and what are your thoughts on how realistic it would be to take this approach for, let's say, a real 3D ship?
Yeah. So my easy short answer is let's not use CFD. Let's use like a blended higher order panel code or something where we could run a sufficient amount of data, and it's already going to allow us to get to the more extreme events. So that's the short answer. Yeah, the cost is still great for generating the data. The data is precious, but can we multiply that data, or can we extend the value of the data through using some of these techniques? We're working on doing the 3D ship problem, but you need to have controllers and movable rudders and propellers, and it's significantly more complex just from the CFD standpoint. Obviously, the cost per sample is going to increase substantially, but we're going to see how far we can get. That's the current word.
Yep. Nice. Yeah, thanks.
Okay, could be last question. Talking to Shimi and in BV about that sloshing, about how to describe it by CFD, that is very expensive. The idea they support is to do first the simulations by very simple model. like fully potential, for example, not CFD but potential, or even simpler, but linearized model, very simple potential linearized model. And then from that model to investigate it kind of in full details, because it's very cheap, so you can go, you can do many simulations. You can cover your region, okay, with high dimension, but with many points, and then to you kind of identify the dangerous domains, and then you go to that domains with the CFD, and you put that you study already in full details and more reliable by CFD, but in limited region. So do you think we can miss something important if you are going that way?
Yeah, yeah, you certainly could miss something important, but I think it's a very good way to go. Yeah, I think it's a very good way to go. Yeah, of course you could miss something, but you want to use your lower order to really span the space. And there are mathematical frameworks in multi-fidelity optimization that allow you to sort of, according to the uncertainty in the model built on the lower order evaluation of the space, to generate new samples, which you can then sample and evaluate with your higher fidelity tools. Yeah, so there are algorithms and frameworks that allow you to do that in a sort of a systematic and more rigorous way. But no, I think it's a very good procedure.
Thank you very much, Kevin, for presentation. Thank you, participants, for the questions and the responses from Kevin, explanations. So we close our seminar. The seminar was recorded, so Kevin gave me permission to record it. I will ask after the seminar Kevin to upload this presentation, if it would be okay, but it should be done formally. And then you and other people who couldn't attend in time the seminar then can watch that presentation and to learn about new exciting techniques. Yeah, thank you very much, Kevin. Thank you all participants, and I'm closing the seminar.
Goodbye, everybody. Thank you.
Bye-bye. First, I stop recording.